The paper addresses the problem of state estimation for nonlinear time-varying systems with uncertain parameters under multiharmonic disturbance. It proposes a three-step solution, starting with the synthesis of an unknown input state observer that requires measurements of output derivatives equal to the plant's relative degree. To relax this limitation, an alternative representation of the observer is introduced. Next, the unknown parameters and disturbances are reconstructed using an autoregression model and the DREM approach, allowing for finite time estimation. Finally, an observer is constructed that does not require measurements of the output derivatives. The motivation for this work stems from the challenges in implementing state feedback in automatic control systems due to the lack of measurements of state variables. Classic methods for constructing state observers for nonlinear, time-varying systems under disturbances have limitations, such as inaccuracies in linearization and the requirement of model linearization and knowledge of perturbation distributions. The proposed approach does not require measurements of output derivatives, and the DREM approach allows for finite time estimation of unknown parameters and disturbances. The effectiveness and efficiency of this solution are demonstrated through a computer simulation. The paper contributes to the development of state observer synthesis for nonlinear, time-varying plants with uncertain parameters under multiharmonic disturbance, which is crucial for enhancing the effectiveness of automatic control systems. The paper also discusses the synthesis of observers for uncertain plants with output-dependent unknown parameters, highlighting the importance of transforming the original system into a linear regression form. It introduces the concept of unknown input observers, UIOs, and presents a novel, comprehensive solution for nonlinear time-varying systems based on the unknown input and the identification-based observer synthesis. This integrated approach aims to address the limitations inherent in each individual method, facilitating efficient operation across a broader spectrum of systems, providing the estimation of the state, with the reconstruction of the parameters and the unknown input in a finite time. The research paper discusses the synthesis of an adaptive observer for nonlinear systems with external disturbances and time-varying parameters. It describes a system of ordinary differential equations with an output signal and an unmeasured state vector, assuming the pair A, C is observable and matrix C has full row rank. The goal is to design an adaptive observer that ensures the estimated state vector converges to the actual state vector and estimates the external disturbance and time-varying parameters in a finite time. The observer synthesis algorithm is provided, including the introduction of an exponentially converging state UIO. The paper demonstrates that the proposed observer is indeed an observer by showing that the error between the actual and estimated state vectors exponentially converges to zero. The proposed observer utilizes auxiliary variables to relax the problem of unmeasured output derivatives, providing an exponentially decaying function and state vector estimate. The convergence speed can be chosen using a pole placement procedure, and the observer can be used to estimate unknown parameters and disturbances. The research proposes a novel approach to estimate initial conditions and disturbance frequencies in systems with arbitrary relative degrees. It utilizes a series of transformations on the original equation to obtain a linear regression form, enabling the estimation of the initial conditions and disturbance frequency. The method involves rewriting the original equation, applying a filter, and transforming it to simplify the sinusoidal signal properties. This leads to a regression equation that allows for the estimation of the initial conditions and disturbance frequency. The DREM method is used to estimate these parameters, involving the introduction of differential equations to determine each element of the vector Kr. This approach is particularly useful for systems where the relative degree is not fixed and can vary during operation. The methodology also involves the use of a swapping lemma to solve problems similar to the case where phi, x, y, t is a linear function of x, t, with modifications for nonlinear functions. The algorithm begins with the estimation of initial conditions and disturbance frequency, then determines the amplitude of the disturbance using Kreiselmeyer's regressor extension scheme, and finally reconstructs the external disturbance f, t, using the harmonic nature of the signal. The state estimation is achieved through the construction of an arbitrary observer of the state vector for the system, which does not require derivatives of the output signal. The observer design for finite time estimation of parameters and states in dynamic systems is presented, utilizing a Lyapunov function v with its derivative derived to ensure convergence of the observer error to zero in a finite time. Theorem 3 states that the observers guarantee the estimation of theta, t, and f, t, in a finite time, while the time-varying observer asymptotically reconstructs the state. A second-order dynamic system with a relative degree r equals 2 is considered as an example, demonstrating the effectiveness of the proposed approach in the presence of measurement noise. The paper also discusses the application of a modified dynamic regression extension method for estimating time-varying parameters in a system with external disturbances. This algorithm utilizes a direct estimation approach to estimate both the initial conditions of the time-varying parameter xi, 0, and the external disturbance frequency omega, t. Simulation results show the transient processes of the algorithms, including errors in estimating the initial conditions of the time-varying parameter xi, 0, and the external disturbance frequency omega, t, as well as the external disturbance f, t. A state observer is constructed, demonstrating robust performance in the presence of measurement noise. The paper highlights the effectiveness of the modified dynamic regression extension method in estimating time-varying parameters and external disturbances, and discusses potential limitations and future work, including the need for solving the Riccati equation in more complex systems and the possibility of reducing computational complexity by fixing the value of x, 0, using the modified DREM algorithm. The research paper addresses the problem of unknown input observer synthesis for time-varying uncertain systems under external multiharmonic disturbances. It proposes a method that enables state vector estimation for systems with arbitrary relative degrees, allowing for the identification of time-varying parameters and disturbances in a finite time. The paper also discusses potential future work, including the extension of the solution to more complex problems such as systems with unknown nonlinear time-varying parameters or nonlinear parameter dependence on the state vector. The paper provides a comprehensive review of existing methods for designing unknown input observers for linear and nonlinear systems. It categorizes these methods into different approaches, including adaptive observers, sliding mode observers, and interval observers. The authors discuss various works on adaptive observers for linear systems with unknown inputs, as well as the design of unknown input observers using dynamic regressor extension and mixing for nonlinear systems. The paper reviews various approaches for designing unknown input observers for specific classes of systems, such as LPV systems and Takagi-Sugeno systems. It highlights the importance of these observers in various applications, including fault detection and diagnosis, and provides a thorough analysis of the different approaches and their limitations. Parameter estimation in multisinusoidal signals is a crucial task in signal processing and control theory. The finite time approach, as proposed by Tien-Kak et al. 38, has been shown to accurately identify frequencies and amplitudes of sinusoidal components. In adaptive control systems, preserving excitation properties in the Kreiselmeyer's regressor extension scheme is essential for parameter convergence. Modifications to the original scheme, as presented by S. Aronofsky et al. 39, have demonstrated improved performance in terms of parameter estimation accuracy and convergence speed. The paper also explores fixed and discrete time estimation via the DREM method, a popular choice for estimating parameters in linear regression models due to its simplicity and computational efficiency. The DREM method's performance is analyzed in both settings, highlighting its strengths and limitations. In fixed time estimation, the DREM method employs a least squares approach to minimize the prediction error, while in discrete time estimation, it utilizes a recursive least squares algorithm. The importance of preserving excitation properties is emphasized, as it ensures the regressor matrix remains persistently exciting, thereby guaranteeing parameter convergence. The paper's findings significantly contribute to ongoing research in signal processing and control theory, providing insights into the efficacy of various parameter estimation techniques. The author's analysis highlights the trade-offs between different methods, underscoring the need for careful consideration of excitation properties and estimation settings in practical applications.